Helicopters have a hard, physics-enforced speed limit. Push a rotary wing aircraft past 200 miles per hour and it loses efficiency, destabilizes, and shakes violently. In 1950, the U.S. Army and Air Force launched a joint competition to bypass this aerodynamic wall. They challenged engineers to design a convertiplane, an aircraft capable of taking off vertically like a helicopter, but cruising at the high speeds of a fixed-wing jet. 3 companies stepped up with vastly different solutions. McDonnell proposed the XV-1, combining a top rotor for vertical lift with a rear pusher propeller for forward thrust. Igor Sikorsky's team took a much more extreme approach with their submission, the XV-2. Their design chased absolute aerodynamic purity by proposing a mechanism to completely stop and hide the main rotor mid-flight. The proposed sequence worked like this. The XV-2 takes off vertically, accelerates forward, and brakes its main rotor to a halt in the airstream. The blade folds 90 degrees, retracts into the fuselage, and the aircraft flies away on stubby delta wings. On paper, this is a perfect aerodynamic concept, but translating that start and stop sequence into physical hardware exposes exactly why mechanical reality punishes overly complex elegance. To understand why Sikorsky attempted such an extreme design, we have to look at the first principles problem of rotary flight, asymmetric lift. As a helicopter flies forward, the advancing blade rapidly approaches Mach 1, generating immense drag. Simultaneously, the retreating blade moves away from the wind. Its relative airspeed drops, forcing its angle of attack to increase until it ultimately stalls. Pushing past these limits causes extreme destabilization. The unequal lift across the rotor disc forces the helicopter to pitch up and roll violently. The rotor is the physical bottleneck. To reach high-speed, jet-level performance, the rotor has to be entirely removed from the aerodynamic equation. Stowing a standard helicopter rotor inside a fuselage presents an enormous spatial problem. Rotors are massive, rigid structures. Sikorsky devised a highly unusual solution, a single-bladed rotor. To prevent the aircraft from shaking apart, a heavy counterweight maintained dynamic balance. Instead of a transmission, compressed air routed through a hollow spar was expelled through a tip-jet nozzle. This propulsion method removed the need for a heavy gearbox. Without a gearbox driving the mast, there was no torque reaction against the fuselage, completely eliminating the need for a tail rotor. The tip-jet hardware physically acted as the required counterweight. It was a highly efficient subsystem that solved 2 critical mass and balance constraints simultaneously. The transition began with the XV-2 accelerating forward in helicopter mode. Once the stubby delta wings generated enough lift, the conversion process engaged. Reducing rotor RPM below 25% caused the flapping hinge to mechanically lock. Aerodynamic braking then brought the solitary blade to a complete mid-air stop. It then rotated 90 degrees and retracts flush into the top of the aircraft. Fully stowed, the XV-2 would operate purely as a fixed-wing jet, theoretically capable of reaching speeds between 300 and 400 knots. But a sequential mechanical process creates severe vulnerabilities. If the hinge lock, the braking mechanism, or the stowage doors failed, the drag would tear the aircraft apart. Early physical testing exposed the harsh reality of the single blade. In 1948, engineers strapped a single-blinked rotor to an older R-4 helicopter. It successfully generated lift, but induced a severe vibration. Wind tunnel data confirmed that stopping the solitary blade mid-flight induced pitch and roll forces completely unmanageable for a human pilot. To counter this instability, Sikorsky evolved the design to 2 blades by 1955. This improved dynamic stability, but exponentially increased mechanical complexity. The airframe now required extra hinges, larger fairings, and heavier stowage doors. Despite this ballooning complexity, the program didn't end due to an engineering failure. In April 1958, with the final contract 80% complete, the Air Force abruptly pulled the plug. The 1957 launch of Sputnik forced the U.S. military to rapidly reorganize priorities. Aviation budgets were instantly diverted into the space race. The converter plane was a financial casualty of bad timing. However, the relentless addition of hinges, blades, and folding mechanisms meant the design was steadily collapsing under its own structural weight. A decade later, the Vietnam War revived the demand for a converter plane. The military needed a rescue aircraft fast enough to reach downed pilots before enemy forces, but capable of hovering over the jungle to extract them. Sikorsky returned to the table with a heavily modified, four-bladed, stowed rotor design. It failed for the exact same reasons. Every folding mechanism and retraction sequence added unacceptable weight and critical points of failure. The ultimate answer to the high-speed rotor problem actually laid in a competing design from the original 1950s competition, Bell's XV3 tilt rotor concept. Where Sikorsky attempted to stop, fold, and hide aerodynamic surfaces mid-flight, Bell chose to simply reorient them. Bell's early prototypes were difficult to control, but the underlying engineering philosophy proved entirely sound. It allowed continuous thrust throughout the transition and directly evolved into the modern V-22 Osprey. The Osprey's design accepts specific aerodynamic penalties. It endures heavy parasitic drag from exposed nacelles and requires a heavier baseline structure, but it trades absolute aerodynamic purity for the undeniable safety of keeping its massive rotors spinning at all times. The legacy of the XV2 is a stark reminder about the limits of design. Elegant aerodynamic theory must always bow to mechanical reliability. In aerospace, simple, continuous mechanisms will reliably outcompete complex, sequential stowage.